hemiacetal formation can also occur intramolecularly, and this is when the carbonyl and an alcohol are contained together within a chain. So effectively what's happening here is the lone pair on this oxygen is coming over here to form a bond with this carbonyl. So let's just number the carbons here. And I'm going to include the oxygen because it's part of a 6-membered ring that forms. And let's draw that ring. So here's 1, 2, 3, 4, 5, and 6. And then on carbon 1, this oxygen that's attached becomes an OH. So what we have here, it's cyclic, but this is a carbon with an OR group and an OH. This is a hemiacetal. All right, so you might wonder, well, why is this important? Well, let me copy this for you so we can add some things to the structure. What I'm going to do is go through and add some chiral OH groups. We have a back OH at 5, a back OH at 4, one at 3, and then at 2, I'm going to put back a CH2OH. And then if we translate this into the product and where all of those groups end up, here's what we get. We have our OH at 2, 3, 4, and then 5 is CH2OH. Okay, if you're not the conversion of this acyclic molecule into the cyclic molecule and doing all the stereochemistry correctly can be a little bit tricky. This isn't something you're going to have to do for this class right now. But if you want to kind of see how that happens, you can build a molecular model of this and rotate around the bonds to get it in the cyclic form. And you'll see how those groups end up kind of alternating between back and out. But the reason this is important is this molecule on the left is the carbohydrate D-glucose. And in the cell, carbohydrates really don't exist predominantly as this acyclic form, but instead they exist in this cyclic hemiacetal form. So this is cyclic D-glucose. And glucose predominantly exists in this cyclic form.